Now that the module is loaded in memory, you can observe the contents in memory. What you can do, you can simply say grep the name of the module. Just put the name of the module. Okay, grep name of the module /proc/kallsyms. I told you /proc kallsyms is abstraction of the entire kernel symbol table, isn't it? The module's members are automatically populated in the kernel's symbol table. So you can see my module has defined a function called init module, cleanup module, klo init and klo exit, right? Why I put klo is because all modules will have this particular artifact. That means the symbol belongs to this module. If you just look up this /proc kallsyms, you get all the symbols in the kernel currently, right? If you scroll all the way down, search for klo over here, you can see this. These are symbols belonging to my module. And now you can see where the symbols are located. They are located in these addresses. These are the actual virtual addresses in the kernel space where my symbols are located. Klo exit function is located in this address. Klo init is located in this address. You can see init module, cleanup module are located in this address. And these symbols are all shown in small letters. You know what this means? You cannot access these symbols from outside this module. These are private symbols. Actually, the name is mangled, but it shows an unmangled name here. The kallsyms is showing the unmangled name. Internally, the name is being mangled. You will see the mangled name in the early versions of the kernel. Maybe if you take 2.6.20, 2.6.24, you will see some double underscore, some checksum, double underscore G, double underscore I, underscore, and you'll see some name. That mangling prefix is also being shown. Today, for readability reasons, for diagnostics reasons, they unmangle and show it in /proc kallsyms. So from the 3.0 kernel onwards, right? So clear with this? Any questions? When you
optimization, let's still get this in.
Yeah, if you enable
Optimization.
You can't enable optimization.
Okay.
You can't use any of the C flags if you know that. But even if you do enable C flags, assuming the kernel is actually built with -O2, -F inline functions and all those things, it is being built with those features. But these functions are not supposed to be inlined. These functions are not inlined. It has to be a function because you should be able to refer to it using a function pointer. Anything that could be referred using a callback handler or a function pointer cannot be inlined. I'm saying it because otherwise you'll not get a pointer to that particular code block, isn't it? So that's why they're not inlined in this case. But other functions could have got inlined. If it's inlined, you'll not see it here. If you are all create one more function, let's say put one more function, okay, I'll do that. If I unload this module, suppose if I say khello, rm mod khello, right? Now if you just say grep khello and /proc kallsyms, it will be empty. The symbols are no longer there. The symbol table is cleaned up, right? Clear? Now one important thing I should tell you. Most of the times, this particular code, what is registered using module underscore init will be driver initialization code. If you write a driver as a module, the driver initialization happens in the module underscore init macro, whatever function registered. Very likely you will go and probe the device, you'll check if the device is there, then you register the driver. So PCI driver, you'll say PC underscore register underscore driver off and you'll provide some driver structure. But after that, you don't really call this function. This function is no longer being called. Once your module is loaded, you'll never call this function again, isn't it? If you believe that you'll never want to call a function again post module load, what you should do is such functions must be defined with a macro double underscore init. If you believe this function is no longer required post module load, just prefix with double underscore init. And I'll show you this. I'll do a build. You know, I have to say make minus capital C and type the whole thing again, right? To make it simpler, I've created another makefile.new. I'll just do one thing. I'll just say mv makefile2. In your machine, you can do that. Makefile.old. Okay, I should make it as old, but doesn't matter. Makefile.new to makefile. I'm swapped this makefile and makefile.new. In this, you can see same line. objfnm : == klo.2. The old makefile also had this. Build this object as a module. Which one? klo.2. And now below I added some extra macros. Kernel directory is equal to /lib/modules of shell uname -r build. So makefiles rule of getting some data, right? This is the kernel build folder. Current working directory shell pwd. I created a default target. When I simply say make, what should you do? run the make command minus capital C kernel build folder subdir is equal to current working directory space modules. You can also say m is equal to also pwd. There's another elaborate way of telling it. Install will install the module, clean will clean up the module. Right? So just see this. I can say make clean, perform a clean rule. See, all the files are gone. I'll rename that make file to .old to old. Yeah, okay. You have still the khello and make file. In the new khello.c, I have just replaced, I've added a macro called double_init before the khello init. Now just observe when I do a build. And I simply say make, it'll build it. I don't have to type that messy -c and all the switches. It's implicitly automated, right? You can take this a boilerplate make file for most of your drivers, out of kernel tree drivers. Okay, so once the module is built, again I'll reload this. I'll say -mod khello.ko. Loaded this module. This time, just see grep /proc /kallsyms. Khello in /proc /kallsyms. Do you see khello in it? But the function was called. Post module initialization, all functions that are marked with double_init, they are disposed of from memory and also from the symbol table. Assign it. Yesterday, if you remember when I was walking through the kernel source boot up, right? Remember many things had a double_init. And I also told you, like, there was something called kernel init freeable, and later on I told you free init mem. I told you that anything that's marked with that double_init macro is marked as cold, cache cold, which means it will be disposed of from memory. So it's a compiler feature which Linux leverages. This will actually conserve memory, saves memory. You will not have a clutter of symbols which you will never use, beyond the initialization. Those things are best defined this way. Likewise, you also have another macro. It is always customary to add double_exit before any function that will be triggered during module unloading. When I say module_exit, I am registering khello exit. You can put that function with double_exit. What is the significance of that?
This will not be loaded initially. Only during RM mode it will be.
Can't be. You load a module, everything should be loaded, right? Everything should be loaded. This has no effect if you build this as a module. This double_exit has absolutely no effect when you build this as a module. But why is it a good practice? When I distribute this module, the target customer who is going to use this module can choose to build it into the kernel or build it as a separate module. When you build a driver into the kernel, can you unload the driver? No, you cannot. So there is no purpose of this function, isn't it? If you choose to build this module into the kernel, this function will not even be compiled. This function will do nothing, will be wired out. Only when you choose a rule to build it as a module, this function will be compiled. But of course, this makes sense provided that the module is distributed to be part of the kernel source code. Now, any kernel module can be part of the kernel source code or outside the kernel source code. They also call it as in kernel source tree or out of kernel source tree. This particular module is out of kernel source tree. You know what I mean by that? The module is residing outside the kernel source folder, isn't it? It is out of source tree module. Any module that's built out of kernel source tree, I do not know if there's any significance of double_exit. You know why? You can never build any module out of kernel source tree into the kernel. If at all I have a driver which is not part of the kernel source tree, there's no way to build a kernel and say this driver must be a part of the kernel. If at all I want a driver to be integrated into the kernel, right, and not available as a loadable module, that driver must be part of the kernel source tree. That means I have to migrate this folder into one of these kernel source folders. Like, if you have the kernel sources, right, it should be in one of these folder structure. Maybe I would choose the right chosen place will be in one of the drivers directory structure. So migrate it there. Migrating there is alone not enough. If you migrate any driver into this, you should also write one kconfig rule. Do you see a kconfig there? What is kconfig? Kconfig is to select your driver. When I'm going to build the kernel from source code, right? You have an option to choose what drivers to build and what drivers not to build. That options are populated by reading the kconfig rule set. So you should also write a kconfig rule. And then the person who's going to build your driver, build your module, can choose whether it has to be built into the kernel or built as a separate module. If he chooses to build your driver into the kernel, right? Any function that you define with _exit macro, the function will not be even built. The functions are simply ignored. Only when you build it as a module, the functions are built. That's why significance of exit macros. Clear with this? Any questions? Doubts so far?
Kconfig is anything to do with menu config?
Yes, exactly. Your make menu config actually reads the kconfig to figure out what entries to print. In fact, kconfig follows a language syntax. There's a language semantics. See this? Main menu, where it has to come. Then it says config source architecture, string source architecture, source so and so. It tells you this. Basically, this is like trying to load all the folders. Kconfig. I'll go to this. Okay, sorry. I'll go to drivers. If you look at the kconfig in this place, shows source all these drivers. So if you add your driver, right, you'll also add one more line, source driver / my driver / kconfig. Let's take one driver's kconfig. Maybe if you take one, any silly driver that's available, maybe char, okay. I'll say vi char / kconfig. See this? Menu, character drivers, source, drivers, tty kconfig, load also that kconfig rules. Config dev kmem, and then give some string message. This will be propped up in your kernel build. When I tell you how to rebuild the kernel, maybe tomorrow, you'll see these things coming up. This has a syntax. This is a language syntax. This is called kconfig language syntax, right? So basically, this is to select a configuration. It shows default is y and is a boolean. That means you can select an option as yes or no. One option indicating /dev kmm virtual device support. Do you want to enable this feature, yes or no? If I say yes, you will have config _ dev _ kmm is equal to y in your .config file. Remember the config file I told you for the kernel build config file? We have a lot of config _ series of macros. So that is created by user selecting many options in this rules. Assigning it. So if you write my own driver, you will have an option to indicate whether you want to enable the driver, disable the driver, or build it as a module. 3 options, tri-state switches. So you'll have config _ khello is equal to y, or config _ khello is equal to n, or config _ khello is equal to m. Yes, no, or module. Now what you do is that the make file which I showed you, right? Remember the make file which I showed over here? In a real world scenario, you will not put objfn here. You know what you do? You will say objfn $config _ khello is equal to khello. This config _ khello will be sourced from .config file. The .config file. The .config file on the kernel build, if at all you have config _ khello is equal to m, it substitute m here. So it becomes objfn. That is build an object as a module. If the .config file says config _ khello is equal to y, build this object into the kernel. So it becomes objfn y. That means when you say objfn y, build this object into the kernel, khello dot.
Where do you define config _ khello?
This config _ khello is defined in .config file. But how does it get a definition .config file? You run the kernel source configuration, like make menu config or make config, right? All of these tools. That will create a .config file. How does that create a .config file? It will prop all these menu operations based on kconfig rules
For each and every driver.
for each and every driver.
From there,
You will either select yes or no or module, and based on the answer that the user selects, the .config file is populated. I'm saying it. This is what the kernel build generally is, right? So in most of your real drivers, that's what you can see. Okay, I'll just remove this. Okay, I'll keep it the same because out of kernel source tree, right? So if I just look up the example here, let's take one of the examples. Let's say char / maybe.
Actually, kconfig is in drivers is there, but it's there in almost net. everywhere kconfig file is there, so
Every folder will have it.
every folder will.
Every driver will have a appropriate kconfig file. Every driver will have its associated kconfig file. So you can see it. Okay, I'm just selecting, like you can see kar/agp, right? Under agp, if I just select a makefile over here, do you see this makefile? obj config underscore agp, config agp li, config, all these are the configuration options. So based on it tells you what .o files must be built as a module. But again, these values are sourced from .config. But who makes sure that these entries are going to .config? The kconfig rules selected during menu-based configuration or kernel configuration. If you look at the kconfig appropriately for this, do you see this? Menu config agp. This will create an option config underscore agp. And it shows tri-state. Whenever you see an option as tri-state, that means you can either be yes, no, or module. 3-state switch. Build this. You can see this. You can say it should say yes. This will be the help system, help for it. In your menu configuration, it will be shown as help. You select help option, right? And you can see config agp ali. Again, this tri-state. Build as a module, build into the kernel, don't build it. So if you look at the .config file generated, there's one .config file. It will not be in the source folder because I didn't do a build here. The build is in the build folder. The build folder will contain .config file. So if you look up user local build kernels and say Linux this particular location, in this you will look up .config file. You see this? All the .config file entries which you see are all selected by me during my kernel build, and these entries were shown by reading kconfig by the menu-based configuration tool. So this .config file is used by the makefile for actually deciding what to build, what not to build, whether to build something as a module or build into the kernel. Clear? It's a huge list that you see here. Some of them will have this, an option as a module. I don't see it. I don't think I built anything as a module in my kernel. It's a monolithic kernel. I've not built anything as a module. But if you look at the real world kernel, right, you'll see a lot of them is equal to M also. Build something as a module. Okay, you can see a huge list over here. Okay. Any questions? Doubts so far? With all these, I just detoured and tell you how the build actually works. I told you the significance of _init, _exit, like two macros. So, clear with this, right? Yeah. Yeah.
The build, how does it choose which option that it has to be given in the build?
You actually, when you're building the kernel, the first rule is to go to the configuration target. You say make menu config, which will come up with an interactive interface where the user selects what options he wants. What to build, what not to build, what drivers to enable, what drivers to build as a module. So those things are selected by the user. Based on the user selection, the .config file is created.
Or we can give it as a command line.
No, you can't give us command line argument because there are like close to 1 million configuration. Million. I'll not say million, at least 100,000 configuration entries exist in today's kernel. 100,000, close to it at least. Every driver has its own set of configuration, right? Assuming there are like several thousand drivers, you can see each of them have their own set of entries. Okay. So this. Yeah, good point. Good question. Remember, I told you when I say lsmod, it lists all the dynamically loaded modules. But if you want to see what all modules are actually there in the kernel currently, which is dynamically loaded or built into the kernel, the right way to look up is ls/sys/module. When you say ls/sys/module, all these are modules. All these could have been built dynamically if needed. But I chose to build most of these drivers into the kernel. That is, all these modules use a macro called module_init. Every driver that uses module_init, right? Every driver must use module_init for setting up the driver initialization code. So every module_init will get a module structure and so on, artifacts, right? All of these do so. So technically, all of these are modules in the kernel. So you'll actually do a difference between the folders that you see here with the lsmod output. See, lsmod output also you'll see that. You can see khello is here. I loaded khello module, right? You see this? Khello is a folder. But every module you'll see a folder. If you observe what's there inside this folder, If you just go to khello, for example, the module that I loaded, you will see some interesting artifacts. Most of them are debugging diagnostics features. Every module you'll see folders like this. In this, most of them are human readable. In fact, you can see this. If I say cat and just specify core size, will tell you the memory footprint of my module. The module's memory footprint is 594 bytes. Memory footprint in bytes. Okay. It tells you what is the init size. This will always be 0 if a module is loaded. You know what this means? The init section, right? Whatever is marked with double_init is all free. Nothing is there in memory. Whatever functions which are there in init section is free. If any function is still running, right, you'll see some size, init size. The init state will tell you what is the state of this module. The module has only 4 states. Let us say it is called as coming, live, going, dead. And after dead is removed immediately. Coming is nothing but, when you say module_int, the module actually comes up. That's like, going live. That means init functions are running. Once the init function finishes, a module is transiting from the init section, init state to live state. I'm saying this, transits to live state. So the module is live. That means all the init sections are now free. When it's a RM mod, it's going to exit state now. That's called going. And then the module is released completely. Actually, there are 3 states. It's actually called as, coming, live, going. And gone is not shown. It's removed. The last state is, the module is not there in memory. Clear with this? If the module is shown as live, that means the module is perfectly active. Why? Because the init section is finished. Until the init section completes, until the init state completes in a module, the module is unusable. That means the initialization function that you have in the module must finish deterministically. That's very, very important. More about it in a while. If you don't finish that, you'll have a broken module. And worst case, you can have a broken kernel, depending on what activity you're trying to perform in the init section. Okay? So you should know this. So it shows the state of this. And then, apart from that, you'll also see other artifacts like, say, what are the other things? You'll also look at ref count. Ref count will tell you the reference count is module. The kernel maintains a ref count. For a module to be unloaded, the ref count must be equal to 0. If at all the module reference count is greater than 0, RM mod, no matter what you do, will not unload the module.